So today I think we'll do some examples, pipe examples. We started out last time on that journey. And so this is relevant obviously for what we did on Friday. We talked about jet levs and major and minor losses in the piping of the system. Don't need to see these guys, see them doing something. And I looked it up last time. Apparently they're 200 horsepower. The pumps or the hardware, which is the umbilical or the power unit that sits on the surface, gets towed behind them. And probably those umbilicals are probably 10 meters, right? 10 meters is 30 feet, 3-story building, 3-story house for order of magnitude. And they seem quite skilled, because I guess some of them were, I was reminded of looking at this in converting the movie on Friday, that some of them are zipping around underwater, aren't they? I thought they show them underwater. Certainly show them looping the loop, doing acrobatics, I suppose. Yeah, do show them underwater. Yeah, cool. It could be your first purchase with your first paycheck out of school. Probably won't be enough, actually. Unless you're very lucky. So, yeah, fine. So, we'll carry on talking about that. So, we've seen that before. What else? I had the sound turned off. Well, I told you that I thought that pipe networks aren't the most interesting thing. They're very predictable and doable because we can get direct answers out of it, very, very straightforward. It's a recipe, so they're nice in that regard. You don't have to assemble things so readily. And they are important, I guess, right? So we've looked at these maybe on the second time we met about the network of pipelines for crude oil coming down from the tar sands in Canada, Alberta tar sands. This must be, it wasn't the XL pipeline, the controversial one that was going to go through Nebraska. I'm not sure whether it went ahead or didn't go ahead. It was, depending on which administration it was at the time. Obama was against it, Trump would have been for it, so I'm not sure what the outcome was. Natural gas, refined products, I guess that's probably gasoline that gets zipped around the country, and maybe CO2. CO2 comes from the front ranges of Colorado and is used for enhanced oil recovery in West Texas. So it's naturally occurring CO2. They pipe it down to Texas, they pump it into the reservoir. It lowers the viscosity and surface tension of the oil and makes you able to recover a larger portion. Some of the network up here in Pennsylvania, one of the big things, of course, is that you want gas, natural gas, in the population centers. And the population centers are focused in the Northeast. So this part of New York State, upstate, I guess is upstate New York, I guess it is, has salt. And salt is used for storing natural gas before it's pumped out in the mornings to satisfy the big need first thing in the morning. So yeah, I guess that's that. And so one of these, I'm not sure which one is best to illustrate the point, but salt caverns, maybe that's not. Perhaps I didn't want that. It's a good picture in there. Well, good enough, right? So one idea in New York State, they have salt caverns. They're not. Some of them are dug out for salt, used as rock salt to halite on roads for the wintertime. But some are also solution mined for the purpose not of getting the salt, but of having storage. And so the storage would be, you drill, actually it's not the best example of this, you drill down with a, you drill down with a borehole, and you just pump water in. It's cased all the way down. You drill it down to the bottom, then you circulate brine around it and recover it from the same wellbore essentially. And so you dissolve a cavern, which is left, typically it might be a few hundred feet tall, 50 feet wide or something like that, like a cigar shape. And then you have gas in there. It could be natural gas for New York City and or the Northeast, or these days it could be hydrogen in the transitional energy economy. And you pump brine in to force the gas out. You have lagoons on the surface, and it ends up pushing the gas out. And then you do the reverse when you're pushing gas in. You recover the brine into the surface lined reservoirs, and then you just flip it. So I used to work at one of those in Alberta, and it blew up one weekend and destroyed some buildings. So I guess you have to be mindful of gas leaks in those things. So anyway, so that's kind of one reason why we might be interested in pipe flow. It's a huge industry in the developed West, in the developed world, I guess, not just the West. So let's carry on with what we were talking last time. I almost got through a class without screwing up. I thought I was quite pleased with myself, but I looked at the stuff this weekend and not so quite, right? So you didn't stop me, of course, but you remember last time we were talking about pipe flow, we're talking about the energy equation. You know all things that you have to know about that is that you write it upstream to downstream. Pump heads are positive for a pump, negative for a turbine, major losses and minor losses. Major losses presumably are always considered turbulent because they're always a constant, not a function of Reynolds numbers. Minor losses are turbulent. Major losses are both laminar and turbulent depending on the flow regime. And the friction factor therefore varies depending on whether you're laminar, turbulent, or transitional between the two. I didn't really mention that, but you see it on the Moody charts that there's a transitional region between the laminar to 2200 Reynolds number, maybe turbulent above 4000 or something, and maybe a transitional regime between them. We can write the equations by summing from a upstream location to a downstream location and accounting for all the components. Typically, these are the velocities in the inlets and outlets. This is the elevations in the inlets and outlets, and these are the pressures at the inlets and the outlets. The velocities, by definition, are the velocities in the pipes, which may or may not be the same. And we can just assemble all those components by just looking at what the individual parts would be. So for this particular cases, the loss terms would be the losses in the pipe lengths from 1 to 2, 1 to 2, 2 to 3, 3 to 4, 4 to 5, which would be these. The individual losses would be at the inlet, if you want to include it, and also at the bends, which would be bend number 1, bend number 2, bend number 3, and the outlets losses if we deem them. We threw some numbers in for these. They were always between 0 and 1-ish. Perhaps a better number would be 0.2, but we used 1.0, probably a bit high. Ended up that these values were actually much larger than the length over diameter losses in the pipes, which are the lengths divided by the 10 centimeter diameter pipe, multiplied by the friction factor for this particular system. And then it just becomes an assembly, and the assembly was wrong because this bracket should be here, and this term here should be outside. It doesn't change it very much. This is still roughly 10, which is what I assumed, but you have 2 added onto it. So this would be 2 plus 10. This is in meters. This is just the height, 6 feet. It's probably more than that, right? 6 feet that you're pumping it up to the nozzle. And if you do that, it comes out to be something like 50 meters. You think if you're pumping up 2 meters, the head you'd need would be at least 2 meters if it's a perfect system, right? You should have a feel for these things. If you're pumping it up from 0 elevation to 2 meters above, this distance being 2 meters, you'd think that the pump in a perfect system with no head losses would be at least 2 meters to get it up there. That's what that really means. And so it happens to be quite a lot more than that. And these turn out to be big numbers. If it was 0.2, then I guess this would be 1 instead of 5. And this number would be a bit different, but it wasn't. You end up with 50 meters. If you convert 50 meters into what the pump capacity was, it ends up being 50 kilowatts. And a real jet lev is 200 horsepower, apparently. I think at 1 horsepower is equal to 700 watts, 750 watts, something like that. So 2 horsepower is 1500, so it's 150 kilowatts maximum. So the capacity of the engine is 15 kilowatt, 150. So 75 is 1500, 150, yeah. 150 kilowatts. And so you'd be worried, I guess, if this number was less than this, because this seems a reasonable number, just from the parameters we've chosen. And so if it was only 10 kilowatts, then this probably wouldn't be right, but it seems like it might be about right. So that's the way of doing it. So we talked a bit about power, etc., in the system and physically what that meant. We talked about inlet losses and outlet losses and bends. Talked about valves and losses in valves. And so maybe we should talk about these extra things today. We'll spend most of the time doing examples, but we'll first talk about what happens if the pipes you have aren't circular. How do we deal with that? What happens if there's turbulence? I guess we've already recapped what we did last time. And actually the example we did last time was a so-called type 1 example. And we'll talk about the formats that we have. Type 1 is the easiest one. You have a velocity and you want to calculate the power or the head loss in the system. It becomes more challenging if you want to calculate the velocity or the geometry of the system, because we don't know what Reynolds number is to start with. If you know what the system looks like and you know the velocity, intrinsically you know Reynolds number. So if the pipes aren't circular, we can get away with doing it just as what we did before. We know that in the laminar regime, we can get the friction factor as a function of some constant divided by the Reynolds number. For a circular pipe, that happens to be 64. You remember that this are your knuckles? Friction factor over Reynolds number. I hate that, but no, I don't hate it that badly. It's like nails on a chalkboard, right? This is friction factor. This is for a circular pipe, 64 over RE. And actually, wasn't you who was asking about transitional flows? Yeah, fine, yeah. So this is laminar. This is turbulent. And this is transitional. We'll look at it in the Moody chart. So anyway, this is what this term is. So the question is, what does this term look like if the pipe section is non-circular? Well, straightforward. You use a characteristic dimension, which is a hydraulic diameter, not the diameter. And the hydraulic diameter is just 4 times the area of the pipe, the red area, divided by its perimeter. So if we swap out for the area is pi d squared upon 4. And we swap out for the perimeter, which is pi d, then we should get something out of it, which is get rid of the pi's, get rid of the 4's, and Bob's your uncle, if you use that expression, is equal to d. Right? For a circular pipe, it backs out as you'd expect it might do. And so that's just a way of getting an equivalent hydraulic diameter, the representative of pipes. You can also get friction factors for these. So everything, like if you use an appropriate Reynolds number, you can use a Moody chart for this appropriate Reynolds number, and everything comes out as it would before. For some laminar, so this is basically saying this. If you want to calculate the friction factor, then you know what if you're turbulent, then everything is importantly related to the relative roughness, right? These curves over here are all a function of relative roughness, epsilon over d. This is a little bit of relative roughness. This is a big relative roughness. And so if you know the relative roughness, you know the hydraulic diameter, and if you know the Reynolds number from a flow velocity, then you immediately know which part of this graph you're on. And so if you're on the right side of this, then you just use the friction factor to directly give you the roughness to directly give you the friction factor. If you're laminar, then you can use this equivalent hydraulic diameter and the Moody charts. But if you have more complex sections, then for laminar behavior, there are actually tabulated values. And so if you have a pipe which is just an annulus with a central core, so the flow is in with this the clear region, then you know that you can get this in the laminar regime, the coefficient 64 for a circular pipe changes from being that for these different magnitudes. So if, interestingly enough, D1 is close to 0, so this central core is almost not there, it should be go towards, bless you, 64, right? It should approach that, but it's actually quite a long way off that. And that's, I suppose, because it means that if you looked at the pipe, and we know that the velocity profile of a pipe, oops, get rid of that. We know that the velocity profile should look like that, parabolic. If you have just a small needle in the middle, then you know that the profile is going to look like this, right? So it's not very close to 64, but I think it's because it's got 0 velocity where it's attached to this needle in the center. If you have it's 0, you'd expect it to be 64 because it would be a circular pipe. If you have a pipe that has a flat flange on it, then I guess it's given in terms of this angle. If this angle is 0, then again you'd expect it to be 64 from what we know. If it's non-zero, I guess if it were 180, I guess this would be 180, wouldn't it? So this would be 180. Then it would be, well, actually it's not too far, surprisingly, off a circular pipe, but it's not the same. And if you had narrow ductwork instead of not circular at all, then it turns out that the limiting value tends towards, if it's A over B is equal to 0. So A over B over 0 means that this is infinitely long. So instead of looking like this, it actually looks like this. So this is when B goes to 0, and B goes to infinity and A goes to 0, right? As it gets wider and wider. And so the limiting value is 64 over RE. So 96 over RE. And you can show that. We didn't do it. If you remember 2 classes ago, we went back to the closed form solutions and we used something like velocity is equal to 32 over mu d squared and some other terms. And we used this to derive the friction factor, which is 64 over RE. So we took the closed form solution for what flow in a pipe was with the velocities 0 at the pipe walls and a maximum at the center of the pipe. If you do that instead of being for a pipe, so this is for a pipe, if you do it for a duct, which is for flow between parallel plates, if I draw my perspective drawing of this, so if you imagine flow between, seems like an esoteric problem, but it's not. You remember my joke of to be or not to be, right? This is the thickness. So if you get the closed form solution for that, This ends up giving you, I mentioned at the time, I'm going down another rabbit hole, a permeability which is equal to porosity times the pore times d squared over 32. For those of you who will use permeability sometime in your future to calculate flow rates through systems. And this gives you a permeability which is 2b squared, I guess. 2b cubed over 12. And 12 times spacing. And you might have remembered that I said if you have a whole bunch of fractures which are 2b wide, but spaced like the rocks on the bypass, spacing of s, then you can calculate the permeability from this. It becomes useful to be able to estimate that. But not for this class. Okay. So that's it. So those are what you might do for non-circular sections. You can always use Moody charts with this, but you can also get, for the laminar regime, some closed form approximate results for laminar only, I guess you should remember. So the example calculations then come into the so-called type 1, 2, and 3 types. And so the one that we did was the simplest. So we know that we describe our pipe flow in terms of diameter, length, and roughness, relative roughness. We define the flow rates either as a volumetric flow rate or a velocity. And we can define the driving behavior as a pressure drop or a head loss. Pump head, I guess, would go in there as well. And so the easiest ones are when we are given, so these represent if we know the velocity, if we know the geometry of the pipe, but we want to determine the pressure drop, then, or the head loss, or I guess in our case, the pump head as well. That's what we did, because that's pretty easy. We know what the jet lev looks like, length of the pipe, assumed some diameters, assumed it was smooth. We did a previous Bernoulli calculation to know what the velocity would be that would lift a 100 kilogram person, and so we know what this is, and we can solve for that. The more difficult ones are where we want to determine the velocity, or we want to determine the geometry of our system, and we only know the other parts. So this would be a bit easier because we know the velocity, so we can get the Reynolds number straight away. But if we want to determine the velocity, perhaps this is I'm not sure it's the most difficult, but it's more complicated. So we'll go through each of those. And so we'll do it probably today and Wednesday. So you know this, upstream, downstream, positive pump, negative turbine, always positive for losses, major losses in terms of incremental losses along the length, minor losses in terms of a loss factor, different characteristics in terms of how they behave, and I'm going to switch to a preordained example, which I'll go through quite meticulously but relatively slowly, and we'll go through what we don't get through next time. So I don't really have a Moody chart for you, and I'm not sure what this stuff is off the top, but the Moody chart contains all the information we really need. So let's do this. So let's work through this. Moody chart. Laminar, left of 2000. So if we take laminar as being this is it. Maybe transitional to here, and then the turbulent stuff begins. We know that for laminar flow, it's a function of Reynolds number, but not of relative roughness, which is this curve here. It's not independent of relative roughness. And we know the converse is true for turbulent flow, which is not a function of Reynolds number, given by the fact that these are horizontal, and that they're a function of relative roughness. Highly rough, smooth. And the bounding value of this is a smooth curve here, which comes down here, which is for relative roughness of 0, which keeps on going. So that's basically the Moody chart. And so if we want to solve this for these pipe flow solutions, we know that this friction factor is actually an Euler number. But we don't really care. We could care, I suppose, but just to understand what it is. And we know that the other controlling behavior is Reynolds number, which has a characteristic dimension, which we now know could be also the hydraulic radius, which we just calculated, if we want to do that. So we've already done a type 1 problem, but let's do another one because it will set up the example we have. So if we take a pipe, and we know that we can take the energy equation and we can either put 2 big tanks on each end. I don't think I need to do that. We can draw, I know you're perhaps scrambling to draw this. We can take it, we did this example as 2 big tanks. We can kind of throw away the tanks, because you know that what we are able to do, water's not going uphill. Yeah, I didn't draw the pipe, right? So this is the pipe. So you know that we can either write the pipe between 1 and 2, in which case we get a delta Z on the left-hand side of the energy equation. Or we could write it as a pressure at 3 and 4. And so we can throw away these tanks. And so we don't need to deal with it. What we do know is if the pipe is a constant diameter along its length, then we know that V3 will equal V4, right? Because the areas are the same. And so we can boil this system down by throwing away the upstream and downstream parts and just saying there's something driving flow. It's either a pressure drop between it or an elevation difference multiplied through by unit weight. This delta P would also be equal to delta Z times gamma, right? So either of these would be driving it. So this is also kind of our head loss that comes out on the other side. So we make life easier for us by having a pipe. It's of some length, it's of some diameter, it's of some roughness. It has an average velocity, it's driving flow, which is the same upstream as downstream, and it's got a pressure gradient it's driving against. And so we can write this equation. This is our energy equation. This is upstream minus downstream pressures. And these are the head loss terms. We ignore minor losses and we just work on the major losses. We can deal with it in both laminar and turbulent, just to see how we deal with that. We've already dealt with that for the jet lev. So let's choose some numbers. Relative roughness of 1 centimeter diameter pipe, 10 to the minus 2 meters. Some velocity, a length of pipe is equal to 1 meter. We need to use either in the laminar regime the Moody chart or 64 over RE for the friction factor, or in the turbulent regime we need to use this. Do them one at a time. So we need to know which regime we are. We need to know Reynolds number. We're prescribing a velocity 10 to the minus 2 meters, which is a centimeter. Density of water, 1,000 kilograms cubic meter. Viscosity of water, for all intents and purposes, 10 to the minus 3 Pascal seconds. Another good number to know is 10 to the minus 5 for air. Not that we're going to use that. Just good numbers to have in your quiver. And so if we keep this as a loose term, we know that Reynolds number is equal to 10 to the 4, which is this term here, multiplied by velocity. Velocity has to be in meters per second, because this term here is in seconds per meter, right? It has dimensions. So this is a useful way to do it. If we want it to be laminar, then we know the Reynolds number has to be less than 1,000. So if we select 10 to the minus 1 for this, 10 to the minus 1 times 10 to the 4 gives us 10 to the 3, which is 1,000. Right? So if we want it laminar, then we have to be at a velocity less than 0.1 of a meter per second, which gives us a Reynolds number of 10 to the 3. Not sure I wrote that there. Head loss is equal to friction factor, length over diameter, v squared over 2g. We could take it off the Moody chart. If we wanted to take it off the Moody chart, 10 to the 3 would be here. And the friction factor would be 0.06 if we wanted to do that. So go up here and then across. That's one way to do it. But here I've just used the friction factor as 64 over Re. That's this term here. Length is 1 meter. Diameter is 10 to the minus 2 meters. Velocity is 0.1 meter squared divided by 2 times 9.81. And it comes out to be, I think these numbers are right, it comes out to be a head loss for this of 3.2 millimeters, if you do the math. Nothing else than that. And yeah, and if you wanted to get the friction factor otherwise, you could get it from the Moody chart, and I guess I'm just quoting what that number is. If you did the calculation with this, you'd come up with exactly the same number. So for laminar flow, you get a pretty, well, not 3.2 millimeter head loss, driving flow. If you want it to be turbulent, we know that for turbulent, we have to be greater than 2,000. So if we juice the velocity by a factor of 10, we end up with 10 to the 4 Reynolds number. This term becomes 1 meter a second, so it's 10 to the 4, no dimensions. 10 to the 4 Reynolds number then gives us this head loss as a function of these, and we need to get what the friction factor is. Reynolds number of 10 to the 4 is this. Bless you. That's a suppressed sneeze, isn't it? So it's 0.025678 9, 0.2529, 0.029, I'd guess. Oh, no, that's not right. So it's, okay, I guess we're assuming smooth. I guess that's the one thing I didn't say. So epsilon over d equals 0, I think. And what did I just say the friction factor was? 0.64. That's for laminar, isn't it? Oh, yeah, fine. So this, I guess, for smooth pipe, friction factor, I said 0.029. Good enough. If it was a rough pipe, it would be a different number. And therefore, if you throw these in, I've done it for a rough pipe, I think by the looks of it here. Length over diameter, 1 meter over 1 centimeter. Friction factor 0.42. Velocity of 1 meter per second divided by 2 times 9.81 meters per second squared, right? 2g. This is 2g. And it comes out to be head loss of 0.2 of a meter. So before it was 3 millimeters, 0.2 of a millimeter is 200 millimeters, right? So the head loss is much bigger to get a bigger velocity through the system. So the head loss was a small number. Now it's a much larger number because we're trying to push it through 10 times faster in essentially the same pipe. It would go through, actually it's not such a difference, right? This would be maybe 50% slower. Friction factors are 50% slower, 50% higher than if it was a smooth pipe, so it doesn't change so much. But the head loss is quite large. Instead of being 3 millimeters, it's roughly 200 millimeters. And so it's a factor of 100 different. And so that's an interesting observation. I guess you could rationalize it that if you look at the friction factors that we had, the friction factor for the smooth pipe for the laminar flow was 0.64, 0.64. For turbulent flow, it's either 0.03 or 0.042. And so they're pretty close. They're not very different from each other. But the head loss is 100 times larger. And so the reason for that is that the head loss is a function of v squared. And you can see from this. So if you increase the velocity from 0.1 to 1 meter a second, you're increasing the velocity 10 times. And so if you change this 10 times, you'd expect the change in velocity to dominate the head loss. And it's roughly correct. This is 200 millimeters. This is 3 millimeters. So it's roughly 2 orders of magnitude different from each other. And so that might inform what you might expect for these things. So that's no different from the Jetlev problem that we did. We knew what the magnitude of the velocity was. So straight away, we could calculate the Reynolds number. And from that Reynolds number, we could calculate everything else. We calculated head loss in terms of instead of everything else. Last time we calculated head loss, which was the major losses, minor losses, and the pump head that was required to drive it. So there's a more complicated example we did last time. Type 2, I guess. Now we don't know what the velocity is. So that's a pain because then we can't calculate Reynolds number. And if we don't know Reynolds number, we have no idea what the friction factor is. And so let's do the same problem from that standpoint. So, same pipe, meter long, a centimeter in diameter. We don't know what the velocity is. Maybe we know the head loss. We know the head loss from above. We had rough magnitudes for that for this pipe. It was either 3 millimeters or 0.2 of a meter, 3 millimeters or 200 millimeters. So this is 100 millimeters. So let's choose this value of head loss. Let's choose a rough pipe, 1 over 100, relative roughness. And we want to determine the velocity. Easiest to get the velocity, but we just need to multiply the velocity by the cross-sectional area if you want to get the volumetric flow rate. So we have our head loss term. This is our dilemma that we don't know what velocity is, but we do know what this is. We can rearrange this term in terms of v squared. So if you rearrange this term in terms of v squared on the right-hand side, multiplied through by 2 times g times d, divide through by friction factor over length, we get this. Square root both sides, we get this relationship here. If we choose a friction factor, so I guess if we're turbulent, is that what I've done here? 0.04. So if we know what the relative roughness is, if we're turbulent, we're on easy street, kind of, right? If we assume we're turbulent and the friction and the roughness is 1 in 100, we know we're here. If we know we're here, then we know that we're on this curve. So immediately we do know the friction factor so long as we're turbulent. So that might be a good way to guess it. And so we know that script F is 0.3, 3, 1, 2, 3, no, these are 2's, right? So 3.2, 3.4, 3.6, 3.8, 4. So this is 0.038. Is that what I've done here? I've used 0.4. This is 0.38. Could be 0.38, but it's not. And if we do that, we get a velocity which must be in meters per second. And so now we need to check whether that satisfies the fact we're turbulent. Reynolds number is density, velocity, diameter over viscosity. We said it was 10 to the 4 times velocity. Velocity had to be in meters per second. So this is 0.7 times 10 to the 4, which is almost 10 to the 4. And so 10 to the 4 would be here. And so indeed, for that particular roughness, we'd be at the right friction factor, and we have the right result. So that's it. And so that's what's going on here. Did I go back in and find it's 0.45? No, not really. It doesn't change very much. If it was a different number, then you'd want to use that again. Or perhaps I'm doing it for turbulent flow. So this would come out. I guess I'm using this. So if I wanted to be completely rigorous with this, 0.7 would be this number here. And it would be this here. So I suppose it would actually technically be this term here. Maybe it's 0.39, 039. I don't know. It doesn't look like it's larger than that though, right? In terms of this. So we have that. So I'm not sure why I'm doing it again, but it turns out to be, if it's not the right number, you just repeat it until you get the right number. Am I doing something strange here? I'm doing it for 6. Yes, thank you. I should get my eyes checked or my head checked. This is it here, yeah, fine. Gotcha. So this is it. So this is 0.7, I suppose, the green curve here, up to this, which is where this one hits, and it comes in at this, yeah. So 0.045, so now I understand. So that's what this is. We do the calculation with that. Velocity changes to give a new velocity of 0.66. Use 0.66 with that. You get a revised value. If you want to go back in to this at 0.66, then you slightly modify this, but not very much. So yeah, so you did have to change it beyond one iteration. So that's what I was doing. So it's useful to assume it's turbulent because it gives you a ready way to get the friction factor, which you really need. So the cycle of calculation is this, right? You assume it's turbulent. If you know what the friction relative roughness is, you immediately know what a friction factor is. And so you have the first step in your calculation. If you know what the friction factor is, and you know you can use this to calculate, if you have a head loss, you can use this to calculate a velocity. If you have a velocity, you can use that to calculate a Reynolds number. If you have a Reynolds number, you can check on your graph to see if that's the correct prediction of the friction factor, and if it is, you stop. You've solved your problem. If the friction factor isn't what it was before, you do a second round re-estimating the friction factor. You get from that revised friction factor in this equation a new head velocity. You use that velocity to get a new Reynolds number. Check the Reynolds number to see if the friction factor has changed. If it's changed, you go back and use that friction factor. So this is the sequence. Simple as that. So if it's smooth, probably the easiest way to do it is to assume it's laminar. Or you think it's laminar, then you can solve in one step, right? It's quite straightforward. So if you assume if you think it's going to be laminar, then you can assume it's smooth. And if you assume it's smooth and laminar, you know that you're either going to be on this curve or this bottom curve here. Easier to do this one because you can solve in one step. So if you think it's laminar. If you think it's laminar, then you know that the friction factor is going to be this. And then this expression that you have here, HL will be equal to 64 over RE times length over diameter times V squared over 2G. you need to be able to substitute into here the fact that Reynolds number is a velocity times a density, bless you, times a diameter divided by a viscosity. And so you know you sit with the velocity in the denominator and v squared in the numerator, you're going to lose one of those velocities. So you'd end up with 64 rho d v over mu times length over diameter times v squared over 2g. We've done this before, right? And I can make it bigger. Don't know why it's so small. So you know that you're going to lose one of your velocities. So one of your velocities, you know you're going to end up with d squared. So you end up with 64 mu over rho d squared 2g is v. And so you know, in our case, we assumed a head loss, so you've got this, and you have every other component that you need in this to calculate velocity. So that's it. So it differs for those systems. So if it's turbulent, then you use the friction factor to get, use the relative roughness to get a friction factor. If it's laminar, you assume it's smooth, and then you can either get it directly from this part of the Moody chart here, or if it's outside, beyond this zone of correctness, you can use this term here just to go up. But it's much easier to get the first estimate for this. I suppose you could check the calculation then to see, now that you have a velocity, you could recheck Reynolds number, and then you could check whether the friction factor that you got before is correct or not. So you can do the same check. That's it. So that's the so-called type 2 questions. That's what they boil down to. So it's about as simple as an exposition as I can add. So just using the Moody charts. Probably don't have time to do type 3, but type 3 gets a bit, let's save for next time. Type 3 is also challenging because you're trying to dimension your system. So you're trying to figure out exactly what the width and height of your ductwork should be for your house if you want to circulate air at a certain flow rate to keep it warm. And so if you're trying to determine the geometry, then the geometry is changing. If the size is changing, then also the relative roughness is changing if you have a given type of ductwork, with a particular roughness in there of, say, riveted, pop riveted aluminum sheet metal, then the roughness of that would be constant, but the relative roughness would change as you change the size of the ductwork to accommodate your flow. So it becomes lots of moving parts and just becomes a bit more difficult to do, more iterative. So. Fantastic. That's it. So, any questions? I did welcome you to the final third of the semester today, week 11. I did mention, just to spoil your weekend, that I posted the review session on Friday, or Thursday actually. So there are 2 type 1 questions in that. Monday and Friday are type 1s. So, don't know that. It just allows you some time to think about these. So type 1s are somewhat straightforward because you start off with a velocity and then you can work directly from that. You can do it much more straightforwardly and with fewer iterations, I guess. So, which is good. Good. That's the essence of pipe stuff. So I'll do some examples, I think, on Wednesday, and then on Friday we'll talk about pipe networks. So you could imagine that in this system, instead of having one pipe going from upstream to downstream, you could have 2 parallel pipes or a branched pipe, and those get a bit more complicated. And those are off this midterm anyway. Those are on the final one, if they exist. So tomorrow's, Wednesday's stuff would be the last one for this particular segment. Have a wonderful day.